This is a pool fire, something that can happen in an underground mine. When we want to perform some fire risk analysis in an underground mine, we will have to consider many cases for the fire to occur, as well as many sources of ignition, including those caused by flammable liquids. This type of fire is also known as pool fire. That is, some type of flammable liquid is spilled and ignited, which generates a fire whose consequences are determined by certain parameters. In the literature developed in this regard, we will find various formulas that will allow us to calculate the intensity of this type of fire. However, many of these formulas require very specific and difficult to obtain data. If we want to carry out fire risk analysis in an underground mine, we will certainly not waste time in overly scientific and rigorous particularities, but we will use some formula that give us results close to those obtained in an experimental way by researchers. In a pool fire, the heat produced is a function of the burning rate of the liquid. There are some mathematical models for calculating that burning rate, and they offer various degrees of accuracy depending on the input parameters. You have the one developed by Burgess et al. In 1961, and also the one developed by Mudan in 1984. However, for the purposes of a fire risk analysis in an underground mine, in which several cases must be studied, using little time for calculations, there are simplified models that provide results close to experimental ones performed. But what is the burning rate? It is the velocity of consumption of the fuel from the pool fire. The mathematical model used with preference to calculate this burning rate is the one developed by Sabetakis and Burgess in 1961 for hydrocarbon liquids, where this symbol is the specific mass burning rate for an infinite diameter. K is the flame absorption extinction coefficient, beta is a correction coefficient for the beam length, D is the pool diameter, X is the combustion efficiency, which we will assume is 1, and delta, H sub C, is the heat of combustion. This equation tells us that the diameter of the fire has a great influence on the burning rate of the liquid. On the other hand, one of the weaknesses of this equation is that most of the data must be determined experimentally. However, in the scientific literature, we can find these values for certain liquids, as you can see in the following table. It is very common to apply this formula to calculate the burning rate for oils that are used to cool electrical transformers, which are devices that are present in an underground mine, and therefore objects of risk for the occurrence of a fire. So let's imagine that the container of this oil breaks and the liquid spills and ignites. To calculate the burning rate of the pool fire originated, we are going to apply the Sabetakis and Burgess equation, and we will find the data for that equation in the table already shown. We will just have to locate the values for, in this case, we are going to use a value of 2 meters for the diameter. After replacing that data in the equation, we will obtain a value for the burning rate, and we are going to enter that value in the software we are using for modeling the fire. That's all for this video, and thank you for watching us. I hope to see you soon with more relevant information. See you.